Hello, my name is Clifton, and today I'll be discussing the topic of collisions. We will be taking a look at the different types of collisions and even a bit of momentum. Before we get further in the topic and some experiments, let us first define what a collision is. Whenever an object in motion comes into contact with another object, it can be called as a collision. The first collision we'll be looking at is an elastic collision. Now, let's see what makes an elastic collision special. In an elastic collision, the objects involved remain separate after the collision, in which they bounce off one another. In this elastic collision, both momentum and kinetic energy are conserved. Some examples of elastic collisions would be billiard balls colliding with one another, the Newton's cradle, and gas particles colliding with one another. One thing to note down is that elastic collisions don't often occur in the macroscopic world. While we may say that collisions like billiard balls or a soccer player kicking away a soccer ball that comes towards them are elastic collisions, these would be considered as more of nearly elastic collisions. However, on an atomic level, collisions are very often elastic.
If not, like so, and he's made it.
Let us now take a look into inelastic collisions, emphasis on the in. Similar to an elastic collision, in an inelastic collision, momentum is conserved. However, kinetic energy is not conserved. Since there's a deformation in the object, there's also a change in energy. Kinetic energy changes into thermal or sound energy. An example of an inelastic collision would be dropping a basketball. When we drop a basketball and do not exert any force in it, we know that it won't bounce all the way to its original height. And sound is also produced, thus the kinetic energy changing into sound energy, thus making it inelastic. And something fascinating is that all real-world drop-to-bounce collisions are actually inelastic. There is one unique type of inelastic collision that we call a perfectly inelastic collision. In a perfectly inelastic collision, objects collide with each other and stick to one another. Examples would include a car crash or a football player tackling one another and going down together. Now, let's move on to some experiments. Our first experiment would have us explore a real-world elastic collision. We call this experiment the tennis and basketball drop. The materials needed would include a tennis ball and a basketball. In this experiment, we'll be dropping a tennis ball and a basketball together. Now let's try to take a look at first at how a tennis ball is dropped on its own. As you can see, the tennis ball barely wants to back up, thus making it an inelastic collision. What about when the tennis ball is on top of a basketball and they are dropped together? Just from looking at it, we can see that the tennis ball bounces to a height even higher than the height it was dropped from. This is because we can say that the kinetic energy is conserved. Like I said before, elastic collisions don't occur in the macroscopic world. This shows as sound is made, which means that some of the kinetic energy turns into sound energy. But this is an example of a nearly elastic collision. Kinetic energy from the basketball is transferred to the tennis ball, allowing it to travel at such a distance. While the basketball also continues to bounce, just with less kinetic energy than it would when dropped by itself. The tennis ball and basketball initially drop at the same velocity. Once the balls collide, the basketball hits the tennis ball and transfers its kinetic energy, thus allowing it to move at a faster velocity. In context to our conclusion, we assume that the impulse due to gravity during the collision is small and insignificant. Momentum is conserved, so is kinetic energy. Thus, the collision is inelastic. Now, let's go into our second experiment, where we will be exploring inelastic collisions. This experiment is called a simple tennis ball drop. For this experiment, we need a tennis ball, a smartphone, and a very handy app called Firefox, which actually caters to a lot of different types of physics experiments. For this experiment specifically, we use their inelastic collisions feature, in which we are able to track the height of bounces, the time between bounces, and the dropping height. Here are the results we obtained from Firefox. We were able to track down 3 different bounces as well as the dropping height and the energy retained on 2 collisions. For this experiment, we need to look at 3 bounces. Then we use the time taken between the bounces that we were able to obtain using Firefox to be able to find the height between the bounces. Since Firefox was actually also able to give us the results for the max heights between bounces, we can then compare our answers. For this, we need to assume that air resistance is negligible. Okay, so to find the height, then we'll use the formula height is equal to half multiplied by acceleration due to gravity multiplied by delta t over 2 squared. At C1, when t is equal to 0.777 seconds, we find that the max height there is actually 74 centimeters, which matches our results from Firefox. And at T2, when t is equal to 0.538 seconds, I found that the max height is 35.5 centimeters, which again matches the results from Firefox. And with the results that we obtained, we were actually also able to find that the energy retained between the first and the second bounce is actually 47.3% of energy one.